Austin, if you don't mind, I appreciate your opening statement and rebuttal. Can I share screen? And I know you have some questions for me on endogenous retroviruses, but I do feel like you guys did not. And if I could screen share, perhaps, Mike. So there's a few more significant questions here. And what I saw from you guys in terms of your attempts to answer the Y chromosome dissimilarity challenge is providing mechanisms, which again is fine. You know, we know these kinds of changes exist: duplications, gene deletion, substitution rate, sperm competition in chimpanzees, for example, can drive mutational changes. But let's start with this question, if you don't mind, Austin or Spaghetti, whoever wants to answer it. I'd be curious as to your thoughts on this. If you're going to invoke, well, okay, we have these mechanisms, but then not model them out, because that's what I'm looking for. Looking for is a sophisticated mathematical model or a population genetics model that is actually showing when these changes occurred, how they occurred, why they occurred, in how many they occurred in. And so this question here on screen: where is the ancestral Y chromosome reconstruction for us to even test if what you're saying can account for the differences? Go ahead. Well, if they want to look at the question, but if they don't, then we can stop the screen share. So it's up to you, Austin. Do you want to look at the question and engage it, or do you?
We can leave it up. That's fine.
Okay.
What exactly were you want to know what a previous version of the Y chromosome looked like?
Yeah. Well, so today we have humans and chimps. You're arguing that chimps are our closest cousin and can be traced back to a common ancestor roughly 6 to 7 million years ago. All right. So if I go to this slide here, it's a good clarifying question. So if we go to this slide here, very interestingly, we have the human Y and the chimpanzee Y. Chimpanzee Y is half the size. It's missing the entirety of its heterochromatic arm. As expected, if chimps and bonobos are related, the bonobo is also missing the entirety of its heterochromatic arm. Heterochromin is important. It's functional. I went over that in my opening. And so the Y chromosomes are less than 30% the same. So you're going to have to explain how these changes came about. You're going to have to model them. Here's your common ancestor, roughly 6 million years ago, right on the screen. So you're just invoking mechanisms, you and the Spaghetti both. That's interesting. It's evolutionary philosophy. Okay, I mean, you could do that.
I
But
think
where's the ancestral Y chromosome sequence here for us to even test if those changes took place? That's my question.
and Austin might be able to know more about this than I do, but my understanding of genes is that they don't leave fossils. So if you're looking for us to make a completely accurate reconstruction of a gene going backwards in time, I'm not aware that that's even possible. All we can do is speculate about what genes looked like in the past, but we're never going to be able to replicate like a Australopithecus Y chromosome because we just can't do it. It's not possible. We don't have access to the information to look back in time.
Is it your position that the ancestor would have been an Australopithecine before the split?
No,
I would say something
Australopithecines were after the split.
Australopithecine-like.
Okay, so what's the best? And yes, you can do it. I mean, you could look at the differences between humans and chimps. You can put out your method, and I appreciate you guys conceding the fact that, again, all we get are mechanisms, just so stories, but we can't even test that if you're not going to provide a sophisticated mathematical model in terms of how these changes occurred, when they occurred, why they occurred. And so, yes, you can do the work, or a scientist can do the work to get a close approximation to what that hypothetical Y chromosome ancestral sequence looked like. And then from there, we can model it out. So, okay, you say we can't get an exact one. Well, what's a close approximation? Well, what's the best you can show us in order that we can have an answer to this question that isn't just evolutionary philosophy?
So, I mean, you're pretty much looking at other species and comparing their Y chromosomes, the ones most related to us, primates. That's what evolution would predict differences stacked up on top of similarities.
Okay,
So
wait,
there's
so
a
is it your
lot of
position? Wait,
similarities. There's a
that's important.
lot of similarities there. The vast majority, the vast majority of the genome is similar. There's no problem for a couple of changes to stack up in the Y chromosome,
Well, that's your
especially
opinion.
when there's such a strong selective pressure for it to adapt because other sperm are adapting, because the female reproductive system is adapting.
Okay, this
I'm
is
not
just
sure. I'm not
evolutionary.
sure what is insufficient about that answer.
Well, everything. It's just evolutionary storytelling. There's no model. There's no sophisticated mathematical model that you're showing. These changes that would have to take place, these are massive changes to the point where we don't have an analog. You can't show me two species, let's say even in the great apes or primates or the lesser apes, where we've seen today or in the distant observed past where Y chromosome differences can accumulate to that amount where you literally, okay, I'll ask you this question then. Why do humans have entire palindrome families? That's a specific sequence in the Y chromosome, and gene systems that are completely absent in pan, in chimpanzees and bonobos. That's what we see in the Y chromosomes of humans and apes. But if they're related, well, then the burden of proof is going to be on you, not to just, again, provide mechanisms. You got to model it out. You got to give us at least some kind of approximated ancestral Y chromosome sequence. And from there, we can say, okay, they've invoked sperm competition, they've invoked gene deletions, they've invoked duplications, so on and so forth, chromosomal rearrangements. Okay, now we can look at that ancestral sequence, do the math, map it out, look at fixation events, fixation rates. But so far, you guys aren't doing any of that. You're basically just saying, well, maybe this, maybe that, and then extrapolating it to say that, well, these massive differences must have accumulated because deletions happen, because chimpanzees are subject to greater sperm competition. These aren't answers, guys.
Why is it that you're focusing so hard on chromosome Y, but not on, say, like cytosome C, like where we have zero differences between, where we have zero differences between humans and chimps? I mean, we share 98.8%.
I feel like you're dodging now. You're trying to get off of the Y chromosome. If you want to do that, if you want to just concede, I already said in my opening statement in the rebuttal, it's the differences that make all the difference. Okay, we can both explain similarities. We can both explain some differences. But when you're looking at this kind, and I noticed you didn't even answer the question, why do humans have entire palindrome families and gene systems absent in pan? Can you just answer that? Just focus on this question. You guys failed on the previous question. Let's try to answer this one.
They diverged from a common ancestor, so it was
okay.
Easy
So you're
for them
assuming they diverged
to follow a mutational path that was different from one another and ended up in different results.
So which lineage lost or gained the palindrome families?
I don't know.
Well, I know you don't know. Nobody knows. Okay, what about the heterochromatin?
If humans and chimpanzees were exactly, it seems like you want humans and chimps to be exactly identical. And if
no, I don't.
Not,
I already said some differences are okay. It's massive differences we're dealing with here.
These aren't massive differences.
These are massive differences. Less than
30% difference in our DNA, and that's it.
No, it's the differences that make all the difference. You're ignoring the massive, even in the Y chromosome paper here. Notice this. They said
we're not ignoring the differences. 1.2% difference is exactly what we would expect to find after 7 million years of evolution.
Oh, so after 7 million years of evolution, notice this, right from your literature, their Y chromosomes differ just a little bit. No, enormously in size and gene content. Notice when you go to the visual here from 2024, take the human Y, bring it up to the chimpanzee Y, you're looking at 26.2%. You can't show us a Y chromosome ancestral sequence. You can't explain the palindrome differences. What about the heterochromatin? How do you explain the massive difference?
The chromosome X? That's what, in the 98, the 80%?
Dude, are you even listening? It's the differences that make all the difference. Yes, similarities is agnostic on both sides. It's the massive. I've noticed again. That's 0 for 2 on questions. How do you address the heterochromatin? What happened to that?
The similarities are what prove that or demonstrate that we share common ancestry with chimpanzees.
You mean because the similarities can go either way. That's agnostic. We're looking at differentiating points, which you guys are dodging. What about this question, Austin? Where is the rate-based population genetic model that shows the duplications, the deletions, the recombination events, and the mutation rates required to produce, according to Spaghetti, There's barely any differences. Okay, let's look. New human-specific palindromes, restructured amplicons, loss of the entirety of the heterochromatic regions in pan. Okay, Austin Spaghetti, give me an analog today where you can show me two lesser apes or two primates, okay, that have lost this much in their Y chromosomes. I'll accept an analog. Show me that, Austin. Do you have one?
Chimpanzees have had intense changes in their Y chromosome. Gorillas have had intense changes in their Y chromosome.
No.
Every primate species closely related to us has had big changes in their Y chromosome
Chimpanzees and
because
bonobos.
they're promiscuous.
Okay, take those mechanisms and model it. Show me this. Show me I'll ask this. Does a model exist that actually answers this question where we don't just have storytelling and evolutionary philosophy, but we actually have a rate-based population genetic model, something empirical rather than, well, sperm
Sounds like you're talking
competition.
about the Hardy-Weinberg equilibrium.
No, so what paper answers this question? Because I can tell you, 2017, they still admitted that sperm competition and faster rates of substitution, gene conversion to explain this goes untested. These are just ideas. These are guesses. But until you actually present a rate-based population genetic model, I'm wondering this, that the heterochromatin, okay? If we go to this visual for the audience, this one should be easy. This is an easier. I get the ampliconic palindrome families. It's difficult for you guys. Okay, what about this one? Here on the chimpanzee and bonobo, you'll notice the heterochromatin. It's completely missing. But on the human Y, okay, in gray here, it's present. Okay, heterochromatin is dense, tightly packed. DNA largely comprises satellite sequences. It's functional in chromosomal stability and gene organization. Anyways, so very clearly not a difficult challenge. Chimpanzees and bonobos, they're basically missing it all. Okay, why are they missing it all? If you're going to say, well, it was lost since the split. Okay, show me the numbers. Show me the model, and also why was it lost? Go ahead, Spaghetti. Let's have you answer this one.
Sure. Well, I like I said, I can't give you, and I've already conceded, I can't give you an exact map of what genes were lost in which year and which organism. What you're doing is you're saying the similarities don't matter whatsoever. They're completely agnostic. You're ignoring the 98.8% similarities in our DNA with chimps. You're taking a magnifying glass to the 1.2% and looking, you're saying, see, look, it's 1.2% different. Look at how different it is in these 1.2%. It's 100% different in these 1.2% differences. And you're completely ignoring all the similarities, not only the similarities, the identical placements of ERVs, which I'd love to go back to, which you think are magically placed there by God instead of being infiltrated into the DNA prior to a split, which makes way more sense. You say your interpretation of
okay,
ERVs
I get it. You're dodging the Y
is,
chromosome. I want to go one topic at a time, no slapping and running. We could go ERVs.